Hi, I'm Mark Barsamian. In this video, we'll be continuing our discussion of integration. We'll be talking about finding a particular antiderivative that satisfies an extra condition. This material is from section 5.1 of the book. More specifically, page 30, example 4 is relevant. The corresponding homework is this collection of 4 exercises from section 5.1. Recall the definition of antiderivative from previous videos to say that a function capital F is an antiderivative of little f means simply that if you take the derivative of capital F, you get little f. And recall that for a given function little f of x, there's a whole collection of antiderivatives of little f. And recall the terminology of particular antiderivative and general antiderivative. Recall that the general antiderivative of little f of x is this function form that is a form that has the plus c, the constant of integration. And that form represents the collection of all antiderivatives of little f of x. What's called a particular antiderivative of little f of x is an antiderivative where a choice of an actual number has been made for the constant c. So we discussed examples where we had 2 particular antiderivatives of this function little f of x equals x squared. And recall the definition of indefinite integral. The indefinite integral of little f of x means the general antiderivative of little f of x. So whatever symbol is sitting inside that integration symbol, the whole symbol stands for the general antiderivative of little f of x. And finally, recall these indefinite integral rules that we've discussed so far. Now, so far in section 5.1, we've been using the following conventions when we discuss functions and their antiderivatives. We've used a lowercase letter for a function like this, little f of x, and we've used an uppercase letter for an antiderivative. So something like this was capital F of x. So you start with little f of x. If you put little f of x inside of the integration symbol, that whole symbol stands for capital F of x plus c, a general antiderivative of little f of x. In this video and in the accompanying homework set, we'll use a different style of notation. We start by knowing the derivative, f prime of x, and we seek to find f of x. This situation can be illustrated by slightly modifying this previous diagram. In this previous diagram, we had a function little f of x, which was used as the integrand, put it inside of an integration symbol, and the result was the general antiderivative, which was called capital F. We'll modify that diagram slightly. In today's discussion, we'll start with little f prime of x. We'll put that inside of an integration symbol, integrate, and the result is little f of x plus capital C. So that's the general antiderivative of this derivative. So we'll be discussing what's referred to in the book as an antiderivative of the derivative. So you start with this thing, you integrate to find this thing. Example 1, A says, find the antiderivative of the derivative c prime of x equals that function. Notice there's actually a mistake here. This should say find an antiderivative, or it should say find the general antiderivative. So again, you can say an antiderivative, or you can say the general antiderivative. We'll find the general antiderivative. We'll do that by integrating. So there's our result, the general antiderivative. Notice we used the constant multiple rule as our first step. Then we used the power rule. And with each integral, we got a constant of integration. Now we couldn't use the letter C because the letter C has already been used. So I used the letter D for this constant of integration. And then I had to use a different letter for the constant of integration over here. And we end up with an expression that has this at the end of it. Now realize that the letter capital D is a constant of integration. It can be any real number. And the letter E is a constant of integration as well. It can be any real number as well. So that means that this circled expression has the capability of being any real number. Well, we might as well introduce a symbol that is more concise that can just stand for any real number. So there's our general antiderivative. Now we can give that a symbol. We could think of that as capital C of x. Let's go back to our diagram. We started with capital C prime of x, and we integrated to get this capital C of x. Now that's a general antiderivative, so it's of the form capital C of x is some expression involving a constant of integration. Let's go on. Question B. This is similar to one of your homework problems. Find the particular antiderivative of the derivative c prime equals 12x squared minus 22x that satisfies this extra condition. Well, the strategy here is first you find the general antiderivative, and then you find the particular antiderivative that satisfies the extra condition. So we found the general antiderivative in step A, and the second part of the strategy is find the value of the constant of integration to satisfy the extra condition. Well, our extra condition is this, c parentheses 0 equals 30. So let's turn that around. Let's say that 30 has to equal c parentheses 0. So we found the value of k. K has to be the number 30. But the question was not to find k. The question was find the particular antiderivative. So now we have to write a clear conclusion presenting the particular antiderivative. And there's our result. Again, we are asked for a particular antiderivative. Our answer needs to be a function, not just this k equals 30. That's not our answer. Our answer is this function. Let's go on. Question C says to illustrate our result on the given collection of graphs. Well, notice that what this collection of graphs is a whole bunch of antiderivatives. Each one of these is a particular antiderivative. They're from that whole collection of antiderivatives. Remember that when you have a function and you find the general antiderivative, what you find is something that represents this entire collection of antiderivatives. And remember that entire collection of antiderivatives looks like this. They're vertical translations of one another. Well, let's remember what our job was. Our job was to find the particular antiderivative that satisfies this condition, c parentheses 0 equals 30. But that means the point 0, 30 will be on the graph. So the way that we illustrate our result is we pick out the antiderivative that we found. The particular antiderivative was this one. And the criterion that it satisfied, the extra condition, was that it's the only antiderivative that satisfies this condition. And we illustrate that by putting a point on the graph there. of all of the antiderivatives, that's the only one that goes through that point. So that we illustrate our result by pointing out that among all of these antiderivatives, this is the one whose graph goes through that point. Let's go on. Example 2. Find little f such that these are both satisfied. The derivative is this, and this extra condition is satisfied. All right, well, our strategy is the same as in the previous problem. We integrate to find the general antiderivative. Before integrating, let's rewrite the integrand. So we put our integrand in power function form. Now we're ready to integrate. So there's our result of integrating to find the general antiderivative. Now again, note that before integrating, we put our function in power function form. So that made the derivative straightforward. We used the constant multiple rule to pull that multiplicative constant 7 right through the integration symbol. And then we used the power rule, being careful with our exponent calculations. Minus 1/2 plus 1 equals plus 1/2. And also being careful with our arithmetic. Dividing by 1/2 is the same as multiplying by 2. And then finally notice the handling of the constant of integration. We have a constant of integration here. We have a constant out front that gets distributed 2 places. So we end up with a 7c. But realize that number c can be any real number. So 7c can also be any real number. So we're at liberty to just simply choose a different name for the idea that sitting in that spot can be any real number. So we're going to use the letter D to denote that. Okay, that's the first part of our strategy. The second thing we do is we find the value of the constant of integration to satisfy the extra condition. Now remember what the extra condition is. The extra condition is here. I'm going to turn that around. I'm going to say 80 equals f of 25. So 80 has to equal 70 plus d. So therefore, d is 10. But our job was not to find d. Our job was to find the function f. So we have to write a clear conclusion. And remember, what we're presenting here is the particular antiderivative. The particular antiderivative that satisfies the extra condition. And there's our result. F of x equals 14 squared root of x plus 10. Let's go on. Question B says to illustrate the result on the given collection of graphs. Well, notice what we've got here is, again, as in the previous problem, a whole collection of functions that are all antiderivatives. They're all antiderivatives of this function. That's my f prime. And so we have a whole collection of antiderivatives of this form, 14 squared root of x plus capital D. And what we found in question A was the particular antiderivative was this one. And what did it satisfy? It satisfied this. F parentheses 25 equals 80. So we have to illustrate our result. Our result was we found that particular antiderivative, but the condition we should illustrate as well. F parentheses 25 equals 80 means that this point is on the graph. Well, let's see, that's here. So among that entire collection of antiderivatives, there's exactly one particular one, that red one, that has the property that its graph passes through that point. Let's go on. This should be example 3. Find the particular antiderivative of the derivative, df dx equals 5e to the x minus 19, that satisfies this extra condition. Okay, well, our strategy will be as in the previous 2 examples. We start by integrating to find the general antiderivative. But before integrating, I want to rewrite the integrand so that it's in a form more convenient for integrating. I want to write that 19 as 19 times 1. Now that might seem silly, but it's important because that is a power function. Remember that 1 equals x to the 0. So now we integrate. Now let's name the thing that we're going to get as our result of integrating. So we're going to integrate our df dx, that's our integrand, and the result of the integration is going to be our general antiderivative. So there is the result of our integrating. We use the exponential function rule for this first integral, and it has a constant of integration that we can call plus c. We use the power rule with n equals 0 to find this indefinite integral. Now notice this has come up before. Let me point out, this integral doesn't have an x in it. We're just integrating 1. But an x shows up when you do the power rule. You don't write 1 to the 0 plus 1. You write x to the 0 plus 1. So there's our result of integrating. Note that we have found the general antiderivative, so it has a constant of integration. And note where that constant of integration came from. There was a constant of integration from the first integral. It was called c. There was another constant of integration from the second integral. It was called d. Each of those numbers could be any real number. So that means that this expression, 5c minus 19d, could be any real number. So we can just replace that with another symbol that represents any real number. So there's our general antiderivative. So we've completed this first part of the strategy, integrate to find the general antiderivative. Now we have to satisfy the extra condition. The extra condition is that f parentheses 0 equals 25. We'll do that on the next page. I'll turn that around the other way. So we find that e has to equal 20. But remember, our job was to find the particular antiderivative. Our job was not to find the value of e. So we end by writing a clear conclusion where we present the particular antiderivative. There's our result. Let's go on. Question B says, illustrate a result on the given collection of graphs. Well, notice what we've got here is a whole bunch of antiderivatives. That whole collection could be considered the general antiderivative. And so each one of those is a particular antiderivative. The one that we found, this one, is the only one that satisfies this extra condition. So we illustrate that by circling the one that we found and pointing out that it satisfies the extra condition. So we have to label that point and convey that our particular antiderivative is the only one of these antiderivatives that goes through that point. Let's go on. Now, if we change the variable to t instead of x, then the problem statement becomes this. Find the particular antiderivative of this derivative that satisfies this extra condition. Well, the result would be it's the same exact answer. We just changed the x from our previous solution to a t. So that doesn't seem like a earth-shattering problem. But let's go on. Now change the function name to x of t, and we get a problem statement that's similar to one that's on your homework. Find the particular antiderivative of this derivative that satisfies this. This can be very confusing. Normally, we have x as the variable and some function name like f or g for the function. But in this problem, we have t as the variable and x is the name of the function. But it's just playing with names. We can just simply copy this result and change the name of the function from f to x. Now you might wonder, why on earth do that? Why do something confusing like having the function named x instead of the variable being named x? Well, one of the very important uses of calculus is to model the movement of objects, physical objects. So in that kind of setting, the variable is t for time, and then you'll have a function that, for instance, can keep track of the position of an object. So that function might be called x if the position is the x coordinate. So this kind of function could be used to keep track of the x coordinate of an object that's moving in time. So this kind of thing comes up in engineering and physics all the time. All right, well, that's the end of that example, and that's the end of the video. Thank you.